Hello friends, today we are going to conduct here the second practical of DC machines and transformers. This practical is related to the Swinburne test of DC shunt motor. Actually, what is the indication of the Swinburne test? The Swinburne test is carried out on the DC shunt motor. The purpose is to find out here the iron loss and copper losses. Actually, this test is also called as a no load test. We are not going to conduct here, or we are not going to put any load on the DC shunt motor. Now what is procedure here? Okay, so procedure is that we have to apply here the rated voltage to the armature. Then okay, so you can allow to run the machine as say the DC shunt motor. You may connect here the one rheostat is series to the field winding, because we have to adjust the speed of machine to the rated speed. Means once we apply here the 220 volt, that is the rated voltage of the armature, is applied across the motor, and if the machine is running at the speed of say 1490, 1492 like this, and we have to adjust here the speed to 1500 rpm. Then by using here the field rheostat, which is connected in the series of the field winding, we can increase the speed to 1500. So once you are getting here the speed at say the rated speed, that is 1500, you apply here the 220 volt to the winding. Then now you measure here the three currents, that is the IL is the line current, next current is the IA is the armature current, third current is the IF is the field current passing through the field winding. Now only single reading you have to take here. Okay, rest of the part is related to calculations only. Now you can calculate here the first as say the armature current calculation will be there. If you measure any two currents, that is the line current and the field current, then the armature current at no load can be calculated here, that is called as IA0. IA0 means armature current at no load condition is equal to IL0 minus IF. Now what is IL0 here? IL0 is the line current at no load condition, and IF is the field current. Now once we have the IA0, okay, so this IA0 can be calculated here, and then we can calculate here the IA0 square into RA. So that is the no load copper losses in the armature winding. So to calculate here the RA, that is the armature resistance, generally say we can conduct here the test. Okay, so we can apply here the very small voltage across the armature winding. Suppose we are applying here the 20 volt across the armature winding. Now measure the voltage, measure the current passing through the armature winding. So means you have the voltage applied across the armature. Then okay, so you have the current passing through the armature winding. Then you can calculate here the RA. Actually this RA is the resistance of the armature, but this is the DC resistance. Now we can multiply this DC resistance by some value, considering here the armature is made from the copper material. So you may consider here the factor that should be multiplied to the RA. So the factor may be 1.2 to 1.6. Now let us consider here the we are going to multiply here the RA by 1.2. So you can get here the new value of the armature resistance. It is also called as effective value of the armature resistance. So this value is multiplied by the current passing through the armature to calculate here the armature copper losses. Now first thing is that okay, so once we have the IA is there, then RE is there. RE, what is the RE? RE is the effective value of the resistance, effective value of the armature resistance. And okay, so what is next thing here? The next thing is that IA square into RE. You will calculate here, or you will get here the no load copper losses in the armature. So once we have the no load copper losses in the armature at say no load condition, we have the no load input. So that is that can be something say measured here by, or can be calculated by using formula V into IL0. So suppose we are getting here V into IL0 is equal to 400 watt. Then okay, so IS0 square into RA, that is the no load armature copper losses. Then okay, so no load input minus no load copper losses, you will get here. So that is called as iron losses. So the iron losses is equal to no load input minus the no load armature copper losses. Then okay, so once we have these losses are called as, or this something say the difference is called as stray losses. So what is stray losses here? Generally stray loss is the addition of the iron losses. Then second is that the mechanical losses, and okay, so third is that the armature copper, the field winding copper losses. These stray losses are the constant losses. Now second thing is that okay, now we have to consider here the, suppose we apply here the load on the motor. You just assume that suppose the machine is going to work as a motor. Now calculate the Okay, so copper losses at different load conditions. So now we can consider here the load condition as 20%, 40%, 60%, 80%, 100%, and the machine is going to work as motor. Now, if the machine is loaded at 20% and it is now going to work as a motor, then okay, so you may simply calculate here. Let us consider here the capacity of the motor is 2.2 kilowatt, 220 volt. Then okay, so it is a DC shunt motor. Now the 10 ampere is the rated current, means whenever we are going to apply here the 100% load, the motor will carry here the current of 10 ampere. Now add the 20% load, okay, so motor may carry here the current of say the 4 ampere. So in this way, whenever the motor will carry here the current of 2.2 ampere at 10%. Okay, so the motor may draw here the current of 1 ampere. At 20%, motor may say carry here the current of 2 ampere. 30% 3 ampere. So like this, you may consider here that 20% load is there. Therefore, the input current is 2 ampere. So if we have the input current, then okay, so if we have the field current, let us consider here the field current as a 0.7 ampere. Okay, so 0.7 ampere is the current, field current is passing through the field winding. So therefore, yes, okay, sorry to interrupt here. If the field current is 0.7 ampere, then okay, you can calculate here the armature current at every condition or every load condition. Suppose we have the load current, or say load is applied, that is 40%, 60%, 80%, 100%. In the proportion of that, we can get here the field winding current. Field winding current will be constant here. At every condition, you will have the copper losses for that particular load condition. So once we are calculating the copper losses at that condition, you have the stay losses, then okay, you can calculate here the efficiency or the output you can calculate here, because input is the input can be measurable here, but the output, how to calculate here the output can be calculated here once we have the input and once we have the copper loss and stay losses, then you can calculate here the output. And if I have the output, I have the input, then okay, so I can calculate here the efficiency. So generally, so to measure here the efficiency, okay, so you can calculate here the, or you can use here the Swinburne test. So Swinburne test is also called as indirect loading test. So by using the Swinburne test, okay, so the efficiency can be calculated here. So this test is the indirect loading test. There are some advantages and disadvantages of the Swinburne test. Advantages are, okay, so it is not needed to apply any load on the motor. Okay, so directly you can indirectly you can calculate here the efficiency of the motor at the different load conditions. But the disadvantage is that okay, so you are not going to apply here the load across the machine. So that's why this method is not so accurate. So that is the advantage and disadvantage. Okay, so you can draw here the graph to complete the practical. Okay, so thank you.